Welcome back to my YouTube channel. Today we'll be dealing with strength of material, which is N6. And then may you kindly subscribe if it's your first time watching my video. And then if you have not subscribe and become the part of the family. Alright, so today we'll be dealing with cantilever, right? Deflection, whereby we'll be focusing on the deflection that takes place on the cantilever. All right, we know that cantilever is a beam that is fixed at the ends. All right, we call that the cantilever. So I want you to understand what is the deflection. We're not discussing deflection is we are talking about the bend. The bend where something is a bend, we call that deflection. All right, so we'll discuss about that. Okay, let's say now we have here the structure. We have the point load. Here I call it W. We have the point load is acting at the free end. We call this free end. At the free end is acting where? At the free end. At the free end of the cantilever. Here at the end. So notice with the hardened details shows you see this band will bend. This theta should represent the band. So if you can try and grab that for that way, it will be like this. That way to now, you will be W. You see it has band. Initially it's here. You see there, but finally this beam due to the point load there, it has band. Here it is. It has band. So you see that the distance, this one between the initial, you see that angle there. So the angle like this band throughout, this is the band. So this band all over that from there until you go there, you see that band, we call that deflection. And then as you can see, the deflection will be at the left hand side, will be here at the left hand side of we have the point load. Our deflection is here. It's at the left hand side. Our deflection, are you together? It's at the left hand side. Here, remember, if you can take this, it has band. This point load is at the end. Still here it's a point load. They did not show, but here it's a point load here. W. So the deflection is where? From from the reference where? You take the reference from the point load. The point load is here, guys. This is the point load. From that point load going until there to the end. The deflection is acting here. Is acting at this side. This direction is acting there. It's on that direction. But if you can check, this direction, we don't have what? Deflection. So take note that you see we have the deflection. So that deflection, of course, will have some angle. It will bend, then will formulate the angle. Remember, this is an angle. We'll have some angle there, which is theta. But where from the left of the point load. All right. So you see we have what? If we have one at the end, if we have at the free hand, if there's a point load hitting at the free hand, you will have one. Check, you'll have one deflection. One. Here we will have a deflection on the left, one deflection. Okay, no problem. Remember, this we can shift this. It's not always will act at the end. Sometimes it can end here at the middle or somewhere there. It can act there. So you must notice the deflection there will always be a deflection that will act on the left. But however, also will have two deflection. But let me not confuse you. You will see what I'm trying to say. So far, when you have a point load that is acting on the end, you'll have what? One deflection acting from the point load until you take it there, multiply by the length until where it is fixed. All right, no problem. You'll have one deflection. Deflection is calculated by what? By this sign represent what? Deflection. All right, that is our deflection. All right, and then check at the end, here at the end, at the free end, the slope is equals to maximum. The deflection there is at the maximum. But here at the end, as you can see here, it is flat. There is no angle there. There is no angle there is no angle, it is flat, like it is horizontal, like if you can take, so the deflection there must be 0. The slope must be 0, even the deflection there must be 0 because it's flat there at the end. All right. So how do we calculate this deflection? Remember the deflection is this one, guys. This deflection, you see that I'm highlighting with purple, with this deflection, this bending that will cause, that is taking place here until there, this deflection, the whole of this deflection will be calculated by what? This deflection will be given by the point load, whereby it's a weight there. You multiply this by the length from the point load, this length from where it's applied until where the cantilever is fixed. Then you don't forget to, this will be raised to the power of 3. You cube that, then you divide this by what? By 3 E young modulus of elasticity multiplied by the length. Here it is formula. Here it is, as you can see, here it is the formula there for the cantilever. Here it is W there, as you can see the delta there, weight multiplied by length raised to the power of 3 divided by 3 E L. This is not L, so guys, this is I, moment of moment of inertia, like this. It's a moment of inertia. So with this we call it the combination of these two, the combination of E and I, we call this the flexural stiffness. The combination of these two, we call this flexural stiffness. All right, so that is what is given. Our deflection will given in meter, so that will be the deflection, the angle there, which is theta. The angle will be given by what? What will be the angle? The angle will be given by, remember the deflection and the angle is different. So the deflection is from there until there. The angle here at the edge, you take the horizontal line like this, then you draw the line like that. This is our angle. At the top you'll have what? The deflection. So we'll have the angle. The angle will be given by the point load or the weight multiplied by length squared. Check the note, 2 multiplied by ELI, which is I, like that. All right. So this is what you have there. This is a deflection formula. So you might encounter situations where now the length, we're talking about now the deflection there. All right. So you might encounter situation whereby the length, now you see the weight, you see we have discussed this one first. When the point load is acting out at the end, at the free end, we call this free end. Here at the end you will have one deflection which will be acting at this direction there, whereby will be acting in that direction, will be acting on that direction. All right, this beam will bend like this. All right, you notice, but now check now here we have we shift this W there. Now we shift the point load, we write it there, we have shifted it from the end, we take it, then we write it here. We just shift. When you shift, once you shift, as long as it's not here at the end, now you'll have two deflections. You must have two deflection. Those two deflection will be the sum, will understand. And then as long as you don't have that, now you'll multiply by this length. Remember, you'll have the deflection from, okay, let me show you this. If you have a cantilever like this, let's say we'll discuss, I wanted to show you. Here it's fixed. Okay, here you have a point load, or you can say weight, but this is a point load. All right, so here we have the length. This is our We'll have the length here. Let me just say the length of this. So, oh, sorry about that, guys. Sorry about that. Then you see we have the left hand side here. Going here, we have the right hand side. So we'll have the deflection here at the left hand side at this direction, going to the left, to the right, to the left, obviously. Then we'll have this going to the right. One, two, three. We'll have two deflection going to this side, deflection that side. Why? Let me show you with hiding detail. This will bend like this. Will develop a bending. As will bend, remember there will be bending that will take place. I want you to check note there. We'll have a bending. So check. Here it's our weight. This point load is this, isn't it? You can write it. It's the same as is like here. So at this direction, still there's a bend. There's a bend in this direction. Also here there's bend. We'll have two deflections. The total you'll take there until there at the end. Okay, I will show you that this one we'll call that additional. We'll have an additional deflection. We call it additional. Wow, my English was going on there. Will be additional. We'll have some additional deflection. We'll have additional deflection if the point load is not acting at the free end. If you have a cantilever, then the weight is not acting here at the end. As long as it's acting anywhere, if you have it's fixed there, you'll have additional deflection. Okay, we'll discuss about this now. We'll have what we call additional deflection. All right, the example here are you given. We'll have additional deflection. All right, let's check. There they say load not at the center end of the cantilever, not the way at the free end. What will happen? We'll have the additional length. You'll have what we call it here. Now we have a cantilever. You see it is placed here. The weight, I want you to check from the left. Take it from here, this direction, from the left. If I'm going this direction, you see there's a bend. This beam is bending. There's a deflection. Also going from now let us take it from here going to the right. You see there's still an additional deflection here. There's a bending. If you can check from here, from B, you see there's a little bending. You can see there's a bending until somewhere here, until there. So we have two bending. We'll have bending this side, also the bending. So the sum of the total of this now those total, this total of this bending, from there you check, we have the horizontal line here, that it's a bending. You see the space. Then we go until where this one ends, the bending where it ends. So we'll have what we call now total bending, because we have two. We'll add them. The left hand side bending and also the right hand side bending. Check here is still bending, is not horizontal. As you can see, if you take the horizontal line, you will see there's a space here. So how to check the bending? If I take the horizontal line like this there, you see, wanted to show something. You see there's a space within this space here. It's a bending. You see, supposed not be a space. You see the space. Also here there's a space that touches there. So there's two bendings. We call that additional bending. This, okay, how do we go about determining this additional bending? The additional bending will be calculated by this. Will be calculated by, you will see the additional bending. All of this now will be additional. All right, will be additional bending. All right, okay, we will have what we call now the additional bending. All right, the additional bending. Are we together? So to calculate this, you'll have now, remember the point load, you'll have the deflection. We said we'll have two. Okay, let's now calculate the deflection. All right, we'll have the deflection, the one from here until we'll consider this side. I highlighted with red the right hand side. So far, the deflection there, the right hand side. We know we have what this is a. Remember, this is a. It's not uniformly distributed. It's just a. It's not uni. We don't have UTL. Remember here we don't have UTL yet. So the bending moment, the deflection will be the point load multiplied by the distance. Remember, from the point load, from the point load until there at the fixed point is the first deflection. We know that will be what? Will be cubed divided by 3 multiplied by E multiplied by I. So we'll have that. That is the deflection. I can call that the deflection here on the what? On the left hand side. Let me just say L like this on the left hand side. However, also we have the deflection on that I can say on the right hand side. Let me just say on the right hand side we have the deflection there. So on the left hand side also have deflection on this left hand side. However, to calculate this one now, we'll call this additional. Now to calculate this additional, we'll calculate this additional. Right? The one that I'm highlighting now. This one, you'll use the whole length. That one with red, we have this deflection, blue and red. So this one, remember, we call that additional. The major one, we focus from here until there, but now this is an additional. That additional deflection, how do you calculate the additional deflection? The additional deflection here is the, you'll be given now the formula to calculate it. This is the additional. It's simply just the additional deflection. Additional, can call it additional. For this additional deflection will begin by what? By theta. Right. Multiply by the distance. What that distance that will multiply? What will be the distance that will multiply now there? What will be that distance? Is the distance, is the additional distance now will be the distance from the point load to the left. Not this side. No. Now to the left. For this additional. For this additional. However, when we are calculating what is this, the angle, the angle, remember the slope, theta, this length is additional, this is additional, this will be additional distance. This will be what will be, this one will be from where is this distance, guys? From this side, from the point load to the left hand side. Are we together? But when you're calculating the deflection, talking about theta, about erasing, when you're calculating this theta, remember, will be given by W also multiplied by L raised to the power 2, remember, divided by 2EL or EI, sorry. Now this length will be the point load. This will be the major point load to the fixed point where it's fixed. If you have a cantilever like this, we have our W there like this. So this you see, that length will be this one from here and going that side. But this one, this additional distance there, that additional distance is from here until to this side, to the additional side. Let us demonstrate that. So we'll have this. So you will add, since you have an additional, you will add and have what? Total deflection. This will sum up, we'll have what we call now total deflection. This it will be our total deflection. Is simply what? Total deflection is simply the total deflection. It's a deflection due to the free load and the additional deflection. In other words, additional deflection due to the ground load. In other words, you'll have, it's the same as you have now. Will be the sum will be have additional deflection this theta means deflection. You see that triangle is a deflection, additional deflection plus the deflection due to what? Due to the point load. Due to what? To the point load, the original one, due to the point load. You understand? Due to the what? To the point load. Now we'll have the deflection. Now we'll have the deflection. You want the total, the deflection due to the what? To the point load. This one is the what? Is the one for the point load, or is the one from going to that side, is the one that you go till to the fixed point. You'll have the deflection at the point load. You add these two, but we know how do we determine this. It is given by what will be, we've just discussed, it will be our slope multiplied by additional length. The length is simply what? Additional is the one that will be additional. You know what I'm talking about. Here we have our plus the point load. We know that the point load is given by W, right? Multiplied by length raised to the power of what? We have our deflection raised to the power of 3. It's a point load divided by 3 EI, isn't it? We together. So this is what we have. But this length, obviously, is due to the point load. It's not the additional length. All right. So you'll have this now. Actual. You understand? So you have this thing. You must understand this. You must try and understand this. You might given the UTL. We have what we call UTL. UTL. You can have UTL. What is UTL? All right. So this is what. So before I'm taking this question, let me just summarize what we call UTL. You understand UTL. All right, UTL it's when you are given let's say now. All right, let's say you are given, you'll be given your you'll be given your cantilever dam. All right. This is your cantilever. Let me. All right. Obvious at the end it is fixed. We know that. So what is UTL? You'll have a distributed load here, like UTL. Let me use some different color. Okay, green. You see, you know this from N4, N5. You've been doing this. If you have all this, we'll consider if you have the UTL. This will bend like that, like this. I will use the hidden details. I will show you. Will bend. This beam will bend in this format. You see, the beam will bend like that. So we'll bend. So the distance here between there until there will have our deflection. All right. Then the angle, you take horizontal line there at the edge. Then you take the line like this. This will be it. But this, however, this is what it's a deflection from where it starts until that bend. So you see, we'll have one bend at the end. So we'll consider we'll have bend at the left. So we know when we'll have one bend like that. So it's clear that we'll have one bend, one deflection. So that deflection, because now it's UTL, since it's UTL is distributed, the deflection will be given by this formula. Now the deflection, they take note, please, will be given. Now we'll have W L raised to the power 4, not 3, divided by 8, E multiplied by I. This is for what? When you have UTL, when you have a UTL, also the slope is different. When you have a UTL, we'll have W L cubed, right, divided by 6, E multiplied by I. It's when we have what? UTL. When you're given a UTL, if you have a UTL like that. So this is supposed to know. You see, we had one deflection. All right. So this deflection, now we can, again, this beam, we can have another cantilever like this. Let's say I have a cantilever there. I have a cantilever. Now this cantilever is the distribution, the UTL is not from the free end. It's just here. Just have it there. You see, now we have the free space here. There is no UTL. There's no UTL. There's no UTL. And then this length L is the length from way of the length where it starts until there. This is the length of the beam. That length that we'll put here when we have that. But now what about this case? You have this case there. If you have that case, so we'll consider this length. Let me just say from there until there. We'll have L. This length now, we'll call this free. This length, you see that I'm writing with white. It's an additional length. It's from the left. This is it will be a deflection from this side. Now it is an additional. It will be an additional length. When now we'll focus on additional deflection, we'll have, we call, you understand, it's just an additional. We have that thing there. That is an additional. All right. We'll have that additional, guys, there. It's a matter of that. All right, we'll have that. But now, when we are considering, if you have given this, how do you calculate the deflection? The deflection, if you are given that now, we want the deflection. The deflection, we know that will be W L. Our L now will write with red to show I'm talking which. I'll use red because you will understand. That means I'm speaking about this length, this L of this distributed, divide by, still the same formula. You still raise to the power 4, you still have raised to the power 4, you still divide, it's still this formula. Still use that formula, E8 EI, right? So that is it, guys. But now, if you have this data scenario that you must understand, let's say now you have now let's say now you have it like this. Now it's just like this. You see, this now will be a problem here. If it's like this, will be a problem. You cannot just say, remember here, you see, we're supposed to, you cannot, will be impossible to just to say like this from there until there. But here we have free. there is no distributed. Now this will be impossible, will be very impossible. So always when you're given something like that, you must make adjustment. What is adjustment? You add, I'll use white. You add your own distributed. You make it to fill up all of this thing. Since you have to do this, you also, because you have added this, you must also adjust the what you have did. You must also take this thing, what to the UTL that you have used here on the top, also write it here on the bottom. You're adjusting, will cancel the one on the top. Let's say we have the force that is going down is 20 newtons. If I want to cancel this force, what I will do, I will put another force that is acting up, which is 20 newtons. This will be 20 minus 20, which will be 0. So here we did not change anything, but we're trying to, if you know maths, we're trying to make some adjustment. Those will be adjustment. We're trying to make some adjustment. So you'll do like that now. You'll have those adjustments. But we'll talk about this, we'll talk about that. We'll see that we'll make some adjustment. Now we'll have the adjustment. Now will be like that. So you can take now the length, the whole length from there until there. We'll have some adjustment now. But all right, we'll see. I'm not there for now. Let us try and do this typical example here. Hopefully you will grasp this. All right, I want you to take something here. This is an I section. Oh, the steel table. I think the steel. Sorry, I did not. I forgot to put the steel table. But in the next video, I will plug the steel table for you so that you can able to use the steel table also. If you are given this, you must know it's an I section, isn't it? You must use the steel table. All right, you must use the steel table to get your I, the moment of inertia. You must use your steel table. How are we together there? All right. So we've given, it says find the deflection at the free end. Obvious. At the free end, you have seen that at the free end we'll have the additional all. At the free end, the actual will be the all of this sum. It will be affecting the all of this. We know we'll have that thing. Here is the load is acting here, as you can see. I'm just adding. You'll have the deflection on the left, the deflection on the right. Let me use another color. We have the deflection here, also have the deflection. So you see we'll have the deflection this side and the additional deflection. So we'll have two deflection. I want you to understand this, guys. So all right, as I say, this, because it's not here at the end, you're supposed to just have, you'll consider one deflection. But since it's not there, it's here, we'll consider the deflection going to this direction, the deflection going into that direction. We'll have two deflection, guys, you know that. And then that will end up having what? The total deflection. The total deflection will be the sum of what? Of this deflection. The deflection at this side and the deflection at this going at that side. We'll sum up these two deflections. So all right, we have the point load. So one thing is amazing. If you have given, okay, you've given this, now I will see we have the mass now. It says parallel flange. Include the weight of the beam in calculation. Young modulus of elasticity is this guy. All right, we have given young modulus of elasticity. Now we say to you include the weight of the beam. When you include the weight of the beam, is like now the weight of the beam, the weight is acting like a UTL. Is like now they're trying to say you will have UTL. Is like this is a weight of what? If you include the weight of the beam, picture it like this. Now we have two things. Be very careful. We have two things now. We have a point load and the UTL. Two things. And then it's is off the beam. Remember, if it's all of this beam, the UTL, it's only one UT. We have one UTL like this. This is an UTL. All right, you must include the formula for UTL. Okay, we'll have our bending. This will bend like that. Will bend this beam. So we'll have the bending at this side. Remember, if I take the horizontal line like this, we'll have, if I take horizontal from that ready, this is the bending. Also, if I take some horizontal line here, we'll have the bending here. This is a deflection again. You see, so if you can take here, we'll have the deflection. So we know, I've shown you guys, you know that we'll have the two deflection. There's no need to explain. There's no need to go in deep. I've explained already. So I don't want to make this video very long, so that I can, all right. So you go to your steel table, you check this on your steel table, right? Then you find your moment of inertia there. So we took it. You find your I there. You're supposed to find that I will be equals to 44,28 times 10 to the power of minus 6. You will get it there on your, it's measured in obvious this is in meter raised to the power 4, but anyways, you'll have that unit there. So anyways, let me include my UTL so that we cannot forget the UTL. So let us find the deflection. We'll have now the deflection will be simply just total deflection at the end here. Actually, when we're counting all of these here at the end, will be simply what a total deflection. All right, so that deflection is a total deflection. All right, will be due to what? To eddy. Remember, we have how many things now? I want you to check. We'll have the, I want you to be careful. We have what? Let me just, before you forget, we'll have deflection due to what? To UTL. Deflection due to UTL. We have UTL there. Let me just say UTL plus the deflection due to what? Do not forget the additional length, because for this point we are focusing on the point load. This point load will have the UTL from that, and also will have what? We are focusing on the point load. Now we are done with the UTL. I've written it. We are done with UTL. Okay, let me just erase it to show now we are done with this UTL. Because I've included it here so that you won't confuse. So you will have the the deflection due to what? At this side there, that we call that additional deflection, isn't it? Yet a additional, I'll just say add like this. Another deflection, I'll use green to show that this deflection now, the deflection there, we'll have that deflection there. This one from there until there, we'll have that one that goes to the right. 3 deflections. All right, let's start by getting the UTL. Already I've given you formula how we go about. Let's find by the start. To find this, we have to find this first also, and you can start. Let me check now the deflection due to UTL. Let's go, because it's always throughout the UTL. It's all of this beam. We said that the UTL is given by WL raised to the power 4, not 3, divided by 8 EI. Right. So check, note the weight. Do we know the weight? But we know that the weight, guys, the weight is given by what? By mass multiplied by gravity. All right. What is the mass of this beam? And then it's given in pair, will be given this weight. It's here. If you're given this, you must understand is this kg. If you can check here, we have what we call the kg per meter. Obvious will be given in kg is 13.3 kg. If you can see, because kg is a unit for mass, so this will be what you take only this portion, 13.3 kg. All right, we have the 13,3. The gravity, obviously, we know that will be times 9. comma 81. What will be this? All right, let me take my calculator a little bit. 13,1 times 9,81. All right, all right. 13, oh, sorry, oh, comma 3. Guys, multiplying this, I'll have 307. All right, 30. I will have 307, comma. Since you are rounding to 3 decimal digits, this will be, remember, we use 3 decimal, will be 0,58. Obviously, we know that it will be in Newton watt per meter. Take note, will be Newton per meter. Why? Is because the mass, it was in kg per meter. Substituted that, we'll have now the weight, and then the weight there. Weight, we use that. The weight is not the point load due to UTL. That is for UTL. Remember, do not make a mistake. It's UTL. Do not use this. We'll use it because we are calculating. Here, we'll use it here on this UTL because now we're focusing on the UTL. Okay, we have that, our UTL. Okay, deflection due to UTL, we have the weight there is 307,058 times the length. Since it's for this UTL is for the whole beam, you'll use the whole. It's for the whole beam. Remember, it's distributed for where? This whole beam. So we'll use the whole distance from here at the end. Going there, we'll have 600 millimeter plus 200 millimeter. It's the same as what is 800 millimeter. So it's the same as 0,8 meter. If you use this in meter, it will be the same as 0,8 meter. But do not forget, this will be what? Raised to the power of 4 there. We have power of 4. We raise this to the power of 4. We divide this by 8. Young modulus, we have given it was 205. You have seen there. Times 10 to the power of minus 9. Right, what about the moment of inertia? The moment of inertia is this one, 4. You'll find this on the steel table. All right, I forgot to put this, but in the next video I will show you. All right, but anyway, we have 4,28 times 10 to the power of minus 6. All right, so that is what we had there. All right, this is what we have now. We'll simply punch this. Here we have raised to the power of 4. Now the change deflection due to UTL. Let's see what we get. Okay, I take my calculator here. I have 307,058 times 0,8 watt raised to the power of 4. All right, then we have 8 times of 205 times 10 to the power of minus 9. Then multiply by 4,28 times 10 raised to the power of minus 6. All right, what do we achieve? Okay, this will be 1,732. All right, this will be 1,732 times 10. I can raise to the power of minus 6. Deflection is measured, is simply just a change. It's a vertical change of length, but it's a bending. Will be in meter actually. So will be in meter. It's measured in meter. So it's due to UTL only. So from our formula, we are done with this part. Let's go to this additional guy as we did. This now we are here now, this additional guy. So we can put that additional guy. Now the deflection due to the additional. So just say deflection due to additional. We know that it is given by what? By theta multiply by the additional length 80. Remember this additional length, if you still remember, will be what? The additional length, we're focusing on this side. Remember the additional is this, you'll use this length is 200. The additional is this side. All right, so multiply by that 200. But now theta, you don't use the additional length. I did not say additional theta. I did not say additional. No, it's just theta. It's theta. So slope, you know that the slope. We're focusing on the point load. Forget about the UTL we're done now. Now you can say W, but or you can say P. If this confuses you can say P as a point load. It's up to you. As long as you won't be confused. As long as you won't be confused. W multiply by the length raised to the power of 3 divided by 2 E L. I remember now talking about the deflection, the slope of due to what for the point load. The slope is for the point load, is not the additional. The slope, you see, the slope will be for the point load. All right, so we have this point load. What will be that point load? You have equal. What is the point load? Here it's a point load. Oh, sorry about that. Let me erase a little bit. You see, point load is what? Is 20 kilonewton. That is a point load. We are using the point load there now for this typical problem, because it's the one that is the point load that is not acting at the end. So 220 times 10 to the power of 3. Remember that was in kilonewton. The length, okay, remember it's not the additional, it's the one, it's not the additional. The additional is the one that I've highlighted with red. Will be this one, the one that I've highlighted with green. From this point until there to the fix will be what? 600. Is simply not additional, it's a straight one. Will be 0, 0.6. 0, 0.6. We have cubed here, cubed all over 2. Moment of inertia was 25 times 10 to the power of positive 3 times I. I does not change. We'll have 4,28 times 10 to the power of minus 6. So this is what we have. What will be now our slope for due to the point load? The slope of the point load. Right, punching this should obtain that. What will be the sky? Slope will be 396,6 times 10 to the power of minus 6. One thing I forgotten, your answer that you'll punch is simply measured in radians, not degrees. It's in radians. And then remember to convert from degrees to radians. You must know that. What do you do there? Do not forget that. All right, if you divide by 57,3, if you want to go from degree to radians. But anyway, when you punch, your answer will be in radians. We have this. So we have now the sky. Remember, we still want the additional deflection. So we have our slope now is 396.6 times 10 to the power of minus 6 times the additional length. Is not this. Do not use 600. You'll be wrong. Do not use 600. Now the additional, your additional is this one. Sorry, is this one. This side, the smaller one. The additional is what? It's additional. It is 200 there, which is 0,2 multiplied by 0,2. Then we'll have our deflection, our additional deflection. Are we together? we'll have 79,32 times 10 to the power of minus 6. Oh yes, is made at in meet. Negative 6 times 10 to the power of minus 6. Yes, meet. This is what? It is our additional. So we have this additional now. What we left with now? The one now. The one. The additional, not of the, we are done with the additional, the original one, the deflection due to the point load, straight due to the point load, not the additional point load, the one that is taking, the one for the point load, exactly, deflection at the point load. This is the deflection at the point load. Now we're focusing on this one now. Deflection on the point load is this guy that I've highlighted with green. Now this side now. Alright, so we know the deflection. Remember I said this will do like this. We'll have the deflection on this side. We are done with this side. If I now will have to focus on this side, the deflection at that side. So far we're left with this one. Alright, we know now that deflection of the point load at the point load we'll have, now we know we have W, our point load, multiplied by length. Right, that length must be aware how we raise to the power of 3. The formulas you must know: 3e young modulus multiplied by I. So what is the weight for the point load? It's still 20 times 10 to the power of 3 multiplied by it. We have seen now that was 600, guys. 600. Remember, from this point load till there, this distance is 600 millimeters, same as 0,6. So we have 0,6 divided by 3. Young modulus is 25 times 10 power of 9 multiplied by this guy, which was 44,28 times 10 power of minus 6. So punching this should obtain that the deflection, I just wrote R, but is due to this exit point load. So this will be what? The exact one of the point load will have 158,6 times 10 power of minus 6 meter. So we are done with so far, but there a little bit, I said it's R there, but you just call it point load when I'm using this equation here. So we can add, we have this now, we have this, we have that, we have this. Now we can have our deflection. Our deflection, let me just say T, or let me just say total anyways. So we know that we have addition, the one of the deflection of the UDL plus the deflection of the additional 80 plus the one of the point load of the point. Let's just add. UDL, it's 1 is here, 1,732 times 10 power of 12 minus 6. The other one, we have them 1, this UTL 732 times 10 to the power of minus 2 plus the one of the additional 79,32 times 10 to the power of minus 2, 7, the other one 79,32 times 10 power of minus 6 plus the one now of the point load. Here of the point load, here it is It's what is 1. It's 158 times 10 to the power of minus 6. So let us find our total now, our deflection. Punching all of that, this will be equals what? Adding all of that stuff there. What are we going to obtain? You'll obtain 0, 0.23 96 millimeter. When you remember the answer that you got, you'll multiply by 1000. So you'll write it in millimeter after you've added those. So this is how you go about. That is it, guys. This is how you go about finding these deflections. This is how you go about getting this deflection. So thank you guys for watching. Just support me by subscribing. Feel free to like and comment and share this to your fellow classmates. See you on the next coming session. All the best.